Alrighty, everybody, welcome back. This is our fourth lesson in our 20-1 quadratic series, where we're actually going to talk about translations. One of the few transformations we'll talk about here. Translation's the first one, and then we'll start to talk about the other ones of stretches, reflections, what happens to the graph if we change the equation, that sort of thing. So in the last time we did this, we talked about the graphs and what we could do with our calculator. So let's just graph this function in here and see what we can do. So we're asked to determine the zeros and y-intercepts as exact values using our calculator. So you can hit your y equals button again and graph your function. So negative 2x squared plus 9x plus 5. You can press graph and see where that gets you. So again, this is good. I don't really need to see that vertex just yet. I really just care about the intercepts right now of the two x's, so those are our zeros. Our y-intercepts, I can see all of those on there, so I don't really care about where the top part is. So let's determine the zeros first. So second trace, option number 2 is 0, and you can find your left bound and right bound. So left boundary, sorry about the yawn. Left bound, as long as you're below, it'll give you a triangle on the left side of that 0. Right side, just above it. So there's one of my zeros when x is negative 0.5. And we can do this one more time on the other side here. So we'll calculate the other 0. And there's my cursor, should be coming around. So left bound, right bound guess, and there is the other one of x is equal to 5. And I think it was in the last video where we talked about we could take something that's a 0, work backwards to find a factor. So again, we solve for this 0 by solving the little factor equation for x. Now I can work backwards here to get it equal to 0, and that should tell me what the factor is supposed to be. Now here, if x is actually equal to negative 1/2, which is what 0.5 really is, well, now I can get rid of this fraction by getting it back to 0, doing everything in reverse. So multiply both sides by 2. So I know that 2x is equal to negative 1. And if you add the 1 to both sides to make one of the sides equal to 0, well, that means that 2x plus 1 is actually equal to 0. So now I know that 2x plus 1 is a factor, right? The factors and the zeros have a relationship in the sense that if you take a factor and make it equal to 0, you can solve for the actual x value. So in theory, I should be able to do that in reverse to get what my actual factor is. So there's one of them. The other one, we can do the same thing. So subtract a 5 on both sides. So now I know that x minus 5 is equal to 0, which is really going to tell us x minus 5 is a factor. So that's great. I've got my two factors figured out already, so I can write this in factored form. The problem is this one has a negative sign in the front. So when I put my two factors together, I should have a negative sign in front as well, because really these two factors build me my polynomial when the negative has actually been factored out of this, right? Really what this looks like is negative multiplied by 2x squared minus 9x minus 5. Essentially, we factored this to get these two factors, but there's still a negative sign in the front. So really in factored form, my function in terms of x says negative 2x plus 1 multiplied with x minus 5. So there it is. And I can graph it to double check. If I only graph the factors with no negative sign in front, I should see the same picture if I did it right. I can put it in factored form here and it will allow me to see it. Okay, and if I graph this, what you'll notice is it's completely, well, it's symmetrical. Let me actually zoom out here a little bit. So we'll make our y minimum a little lower. So let's go minus 20, and our y maximum will go plus 20. And what you'll see is the graphs are symmetrical, but but they really are supposed to be the same picture, and it's the fact that this negative sign wasn't there that's going to flip over our graph. So if I go back to my y equals page and I notice that, hey, my negative sign's not in front of my factors, if I actually insert it into the front and then hit graph, well, this is where I'm going to see just the one picture, because now the two things I graphed were identical. So I do need that negative sign in the front because this opens downwards, so I do need that in there. Okay, so I've got it in factored form. We found the intercepts. We just need the y-intercept, and using your calculator you can press second trace and insert a value, and what you want to put in is a value for x. And if I know I'm looking for a y-intercept, well, the value of x I care about is when x is 0. Every y-intercept has that in common, so if I hit enter, it will tell me that when x is 0, the y-intercept is 5. Okay, so for your y-intercept point, x is 0, y is 5. Which is perfect because that 5 is also the constant in my original function. Right? Whatever the constant is going to be, that's your y-intercept. So I didn't need my calculator. Really, I could have just looked at the equation, but there's another way that we can take care of this. Okay, quadratic equations are going to be written in multiple forms. There's two that are really going to be important for us. One of which is called general form, which really looks like the polynomials you saw a lot of in Math 10, the ones you can factor. But then we're going to talk about a new form, which is called standard form, which will tell you, a lot more about this parabola, about this quadratic. So that word I just used, parabola, that's the graph of a quadratic function. This curve that you see on this graphing calculator here, that graph we call a parabola. That's the name for it. It's a parabolic path or a parabolic shape. The vertex of it is either the highest or lowest point. So depending on which way this graph opens up, does it open upwards in the sense that the two end arms there, do they point up or do they both point down? So if it points in a downward direction, really it kind of looks like a sad face, which means there is a maximum to this. There is a place where it stops getting higher and starts to come back down. So we would say this has a maximum. If it was flipped over, kind of looks like a happy face, so it opens upwards. Well, there's the smallest value that we could have, which we'll call a minimum. So it really depends on which way the graph opens. There's something called an axis of symmetry as well. All these parabolas are symmetrical around a certain point. And it's the vertical line that intersects the vertex at peak or valley, right? The highest or lowest point. And so the symmetry line will intersect the vertex. Essentially, it cuts it right down the center, right? It cuts it in half. Now, I can't do that symmetry line horizontal because the bottom and top halves of this graph aren't the same. But the left half and the right half are the same. So I can cut it vertically, and that is what my axis of symmetry is going to tell us. Okay, and it's a vertical line that's important, and every vertical line shares the same format. They're all x equals lines, and they all go through the vertex. Now, when that coefficient of your squared term is positive, your parabola will open upward. So the one that's on the graph here, this one had a negative coefficient of x squared, so it opened downwards, right? It was negative. We have to also talk about domain and range again, where we talk about the domain of a quadratic function. It really could be any possible x value, right? No matter what number you put in for x, you will get a y value associated with it. Okay, so any real number is good for your domain. For your range, however, not every y value will work. Right? If you think about the one on the calculator here, there is a maximum to this, which means there are certain y values that are bigger than it that I will never get on the graph because this is the maximum point. I can't have a y value bigger than it. That's literally what maximum means. So all these things we can talk about as they relate to a graph. So here's an example, and this one opens upwards, right? So I know I have my arrows there. It tells me it goes up forever. It tells me it goes left and right forever. There's a couple pieces to this which we'll talk about. So it says, what is the equation of the axis of symmetry? Draw it as a dotted line. So we'll draw it first because it's the symmetrical line that cuts this down the center. So there it is in red, right? There's our line of symmetry. And you can even put the arrows because it is a line. And the equation of it, that axis of symmetry is always going to be an equation. And if it's an equation, it should have an equal sign. Now, that red line that I drew, the red line that I drew there is going to be our vertical line that goes through the x value of 1. So I know every point on that line should have the same x value, and that is the line x is equal to 1. Right? It is an equation, so it should look like 1, but there's my vertical line of x is equal to 1. Okay, what are the coordinates of the vertex? And label it. Just make this a little larger. Okay, what are the coordinates of the vertex? And label it. Well, I can see my vertex on this graph, so we'll do the things in different colors here. So we'll do it in pink. Right, there's my vertex. It just happens to be the lowest value that exists on this parabolic curve. So I know that the coordinates always follow the pattern of x first and then y. So I know that it's going to be 1 minus 4. That's going to be my vertex. Okay, so the coordinates of the vertex are 1, negative 4. Okay, I can see it there. And we can also talk about that vertex as being a maximum or a minimum and what its value is. So if this is the graph, again, that is the lowest point on that graph. There's nothing underneath here. There's nothing smaller than it. So I know that is a minimum. Now, when it talks about the value, well, this is a function, right? So essentially, this is the graph of y is equal to f of x, right? I don't know the equation of it. It is a function, so I know that if I input x to this, I get out a y value. So if I input the value of x as being 1, the value I get out of it is negative 4. So this minimum exists at a value of minus 4. Okay, that is the value of your y, that is the value of your minimum. We can talk about domain and range as well. And it does say in set notation. So domain's the easy one, because in set notation, the way it looks, you'll have a curly bracket to denote the fact that you have a set, and it's the set of x values given the restriction that really there's no restriction, because any x value is okay. So we can say that x belongs to the set of real numbers, and we can close our set. Right? So this is the set of all possible x values given the restriction that x belongs to the set of real numbers. It's a fancy way of saying there's no restriction. X can be whatever you want. If you think about range, well, the notation is basically identical. So the set of y values this time, given the restriction, and I had a minimum here. The lowest y value on this was minus 4. So it can't be every single y value. All of my y values have to be greater than my minimum, because that's literally what the minimum means, it's the lowest, but I could also be equal to my minimum. Right? It could be equal to minus 4. It's a point that exists on the graph, right? I can see it. Other than that, I have to be larger than it. I have to be above it. So I have to be bigger than it too. So greater than or equal to minus 4. Other than that restriction, y still belongs to the set of real numbers, because it can be anything else as long as it's greater than or equal to minus 4. Any decimal, any fraction is okay, as long as it fits in that range. All right. We could also talk about what happens if we alter the equation to this. So usually we can compare things to the generic parabola of x squared, right? That's the one where nothing is applied to it. So what these really talk about is what happens when we move the graph, right? When we change what the equation is, what happens if I put in some extra numbers. So this is the effect of changing what we call q in y is equal to x squared plus q. What happens if we add a constant to the end of this? What moves, right? And the constant is always going to be your y-intercept. So in the original graph of y is equal to x squared, that I'll do in red here, the vertex, or y-intercept in this case, is right on the origin, right? 0, 0. Now if I change the graph and I make it y equals x squared plus 2, those extra 2 units will tell me where my y-intercept is now. So this point is now 0, 2. It went 2 units upwards. The whole graph shifts up. So every single point moves 2 units upwards. The vertex is just an important one that we'll talk about. But every point moved up 2 units. If I made that a minus sign instead, well, instead of going up 2 units, we're just going to go down 2 units. This example has it as a minus 3. So your vertex originally, here it is in red, 0, 0 again. And if you change the equation and make it y equals x squared minus 3, well, again, there's your y-intercept. It's changed now. The coordinates are 0, negative 3. It just went down 3 units instead. Right, so the constant number on the end tells you where your y-intercept is going to be. Positive means you go up. Negative means you go down. You could also go left to right. And this is where people usually have an issue in the sense that it's opposite and counterintuitive to what you think it should be. So the graph here, y equals x minus p, that's in brackets, squared, is the image of the graph y equals x squared after a horizontal translation of p units. The key here is recognizing that the negative sign, in this top part in pink, the negative sign is built into the equation. That's the key. So really, I'll give you an example. If it's y is equal to x minus 2 squared, well, the negative's built into it, so really I'm going 2 units to the right. It's just counterintuitive because it looks like it's a negative 2, and negative meant go left on every coordinate plane that you've seen since like the 4th grade. But here, if the negative sign is built in, really that means that the value of p is positive 2, which means go right, which is counterintuitive to everything. So when you see it as a minus sign, you got to remember that it's actually opposite to what you see. So if I'm going to go for this one, it even has a 2 here. So that is a negative sign, but that negative is built into the equation, meaning that p here is actually a positive 2, which means we're going 2 to the right. If you happen to see a positive sign in there, well, it's backwards because it really should look like x minus, remembering the minus is built into the equation, but you're subtracting negative 3 in this specific example anyways. And the reason why you see it as a positive is there's a double negative that will simplify, right? It'll cancel out and turn into a positive. So really what this says for you is that p is actually the value of minus 3. That means you're going left because it's negative, which you can see on here as well. So it is a little backwards, which causes people some problems. So think about our base quadratic function of x squared. Nothing's really happened to it. There's nothing being added or subtracted. Write an equation which represents the function with the new input of x plus 2. We take that function and then subtract 4. But if you remember how function notation worked, what we can do is put our new input in. So I know that f of x is x squared. So if I do f of x plus 2, let's just do that first. That's the new input. Well, if I put that into f of x, well, that says I'm going to do x plus 2 squared. Wherever you see x, replace it with your new input. So I get x plus 2 squared. And then what we'll do is minus 4. So then if we do f of x plus 2 minus 4, well, I already know what f of x plus 2 is. It's x plus 2 squared. And then we can minus 4. So I've got my new function. Here it is. There's my equation. I just applied some transformations to it. B says, predict the transformations on our generic y equals x squared that result from our altered equation. So essentially, what transformations did we just do? Verify it with our calculator. So if you were to describe those transformations, we moved the original graph. So I'll graph the original. So let's clear these out. So here's x squared, and then if you hit graph, right, there's just the base one, right? Vertex on 0, 0. Let's even go back to normal grid. So vertex on 0, 0 at our standard 10 by 10 window. But we've altered the equation in part A. So if we list out the transformations that we did, well, I know I'm going to have horizontal translation. So there's a horizontal translation of 2 units to the left, because I can see it as an x plus 2, which is really like seeing it written x minus negative 2 squared minus 4. So the fact that it's a positive means there's a negative in there to cancel out the original negative from the formula. So I know that value for p is negative 2, so I'm going 2 units left. In the sense of a vertical translation, the other value, we are going to move 4 units in a downwards direction. Okay, so 4 units down. So I know that if I graph this, what I should see, and you can put in just x plus 2 squared, that's in brackets, and then our minus 4. What I know I'm going to see is that original graph moved left a little bit and then down. So I know my new vertex is going to be not 0, 0, but it should be 2 units left of that. So I can write the vertex here. I know my new vertex is going to be 2 left from 0, which means it's at minus 2. 4 down from 0, so it should be at minus 4. So let's just see what happens if I hit graph. Okay, so it is moved. Let me change. If you didn't know, you can change the lines and thickness and what they look like. So if I just go to the left and hit enter, I'll make this one a bolded one. So if I hit graph, it really shows how different they are. So there's the original. There's the new one. My original vertex, 0, 0. And, you know, I could move this around to see if I get x on 2 and down a little bit. It won't be perfect. But it'll get you like pretty close to your vertex, which is right around negative 2, negative 4. So we'll talk about calculating that a little bit later, but it is something we can do exactly using the calculator. So we predicted our transformations. It looks good. We've got our vertex, and it comes straight from our equation, like we said. So the values here, the numbers that we used, are going to tell us our vertex in this equation. So in this standard form of a quadratic equation, this will essentially tell us the vertex every time. The vertex, we stated it already, so let me just move this to where it's supposed to be. So there it is. There's the vertex. Maximum or minimum value. Well, let me take out the original one, just graph the new one. I know this opens upwards, so I know there's a point where it won't get any lower, so I know this is what we call a minimum. So it's a minimum at a value of minus 4. That's the y-coordinate of this vertex. The lowest value it will reach after having an input value of minus 2. So when x is negative 2, y is negative 4, and that's the lowest y value that exists. What is the equation of the axis of symmetry? Well, if I know what the vertex is, that axis of symmetry is a x equals line. It's vertical that goes through the vertex. So it'll always be your x-coordinate of your vertex. Those are what those two numbers tell you. The y value tells you your minimum, the x value tells you your axis of symmetry, tells you the line that will cut it directly in half. Okay, how is the vertex related to the equation in standard form, and can you easily tell what the y-intercept is? Well, here's the equation in standard form once again. Y equals ax minus p squared plus q. A is a value which we'll talk about in the next lesson. It deals with, you know, how stretched out or how compressed the graph looks. So there are ways we can alter this graph, the shapes of them. That's what is controlled by that value in the front. But your vertex basically comes from these two numbers, p and q. Some resources call them h and k, but they do the same things. That's your vertex. Right, so if you have it in that equation, so the coordinates of p and q, that's the vertex. Right, p is your x-coordinate, and q is the y-coordinate. Okay, that's what those tell you. Okay, there's a couple things we'll do here before we wrap this up. So if we take a look at these equations, these parabolas, they are different than the base one of x squared. So there are some transformations that happen to it. We're just going to list out what they happen to be. So for A, there is a number attached to the x in that set of brackets. So I'm going to be looking for a value for P here. So if I rewrite the equation, that's really like saying it's x minus negative 10 squared. So really the number in there is a minus 10, and since it's negative and it's attached to x, I know I'm going left. So you've got a horizontal translation of 10 units left. Okay, that's what the negative tells you, 10 units left. For B, you don't have a number attached to x squared, but you do have a constant. So not a horizontal translation, but a vertical one. Of 4 units up. I know it's up because that's a positive. So I know that the original vertex on the x squared is at the origin, 0, 0. The fact that this is plus 4, well, I know my y-intercept is now going to be 4 units up from 0 at positive 4. Which means every point just moved up 4, because the whole graph will move. If you think about C, well, it doesn't really have the same format as my generic standard form equation, which again, here it is in red. Right, so there's nothing usually attached to y. So this time I've got a number to move here first. So I'll subtract an 8 on both sides. So y equals x minus 5 squared minus 8. So now I have it in the same format where I can see what my vertex is. So now I can describe these. So I've got a horizontal translation. Translation. 5 units to the right. And we've got a vertical translation. 8 units downwards. So I do have two transformations, two translations that happened. There's my directions. Okay, number 2, the last couple things on here. The following transformations are applied to this graph, x squared. Write the equation of the image function. So the image function is just the new one after the transformations have been applied. So if we start with our x squared and think about what we're doing, right? The A says we've got a horizontal translation 5 units to the right. Well, I know that if it's horizontal, it should be attached to x. And if I'm going to the right, that means P is positive, which means I've got a subtraction sign built into the equation. P is positive, so I'm putting in 5, and it's squared. There is my equation for this image that shows a translation of 5 right. And you can graph this to check. Right, so x minus 5 squared, graph. The original one should be 0, 0. The new one, 5 to the right. Okay, so there it is. There's what it looks like. For B, we've got 2 transformations to deal with. So we're going to go 4 left. So if right means negative, left has to be the opposite and go positive. 6 down. Well, we said positive ones on the end went up, so 6 down means minus 6. Right? And you can determine your vertex just from that information. If it's 4 left, there's my minus 4 for my coordinate. 6 down means minus 6. Right? So there's the vertex. The vertex for the one above is going to have an x value of 5, y value 0, and I can see it right on the graph. Last one here, number 3, what are the coordinates of the image of the point 3, 9 on the graph y equals x squared when a translation of 2 up, 7 right is applied? So I know this point 3, 9 is going to be on the graph of x squared. I just want to see where the new one is going to be. So if I start with 3, 9, and I do 2 units up. Okay, here's for our first translation, 2 up. Well, my new point will still have an x coordinate of 3, because that's a vertical motion, so the x coordinate's not changing. But instead of at 9, it'll be at 11. Right, so there I've reflected my 2 units up in this, right? I've got that transformation applied to it, and then we'll apply the other one, 7 right. So if I'm going right, I know my y value is not changing, so it stays at 11, but 7 to the right of wherever 3 is, well, that's 10 now, right? 7 units to the right of 3 takes you to an x value of 10. So I know now that point is going to be on my transformed graph. Right, so there's the image of the point, and you can determine this. You can even make the equation. Right, so if the equation is going to be, if it's 2 units up, 7 units right, well, that means the image function should be y is equal to x 7 units right, so x minus 7 squared plus 2. Right, there's the image function, and here's the image point. So those two things, well, this point should be on this graph. So if I graph this, x minus 7 squared plus 2, and hit graph, there's what it's going to look like. And I know my window settings only go to 10, so I'm going to make the y maximum larger. I'll do 15. And the x maximum, I'll make it 15 as well. Just give us some more space. So I know that if I find a value by hitting second trace value, I can put in an x coordinate. So if I put in the x coordinate of 10 and hit enter, it should tell me 11, because that point should be on there. And there it is. Right, so I could do all of that without the calculator. It's really just adding some numbers together. But I know my image function, I can represent it in that standard form. I could then check my calculator to make sure that the value of x when it's 10 gives me a y value of 11. So I know I did this correctly because I can see it on the calculator. Okay, all looks good. Is there a way to get the coordinates for vertex from general form without what's called completing the square? We will do that a little later. And one of the ways you can do this, well, really the only way you can do this, is if you know where the axis of symmetry happens to be. Because if you know what the axis of symmetry is, it tells you the x value of the vertex. So what you could do is, if you know where the symmetry line is, you can plug that into this, and it will give you what the y coordinate is going to be of your vertex. Right? If you know your symmetry line, it will tell you where your value for that vertex is going to be, either minimum or maximum. Right? If you know the symmetry line, plug in that value of x, and then you can get the y value that's supposed to match with it. At this point, that is the only way that you could do this. Later on in the next few videos, we'll talk about something called completing the square and what that will allow us to do. It's a whole process that will basically allow us to jump from one form to the other. Either general form to standard form will be the way that we could do it. So this basically is one of the more challenging things, because of the fact that that x, the sign is backwards, to really tell you which way you're going and traveling around the plane. But once you sort that out, it's relatively straightforward, and not a lot really changes. The same principles get applied to functions in Math 30, especially in the trigonometry, logarithms, exponential functions. The same transformations are true, and the same rules apply. So if you know one of them, you really do know them all. So I'll have all the resources, which you already know, that'll be in the description box, full key, blank copy as well. So let's wrap this one up, and we'll see you in the next video. Take care.